So, the second day, guys, about paleoecology, and I want to look with you to examples of convergence, because as we said yesterday, paleoecology is about the relationships between different species and interactions with their environment, and we can see that during evolution the environment influenced the way of evolution, and you can still see that today. If we look at these birds who cannot fly, does everybody know every bird on this slide?
It's emu, Lloyd's ostrich.
Yeah.
And it's a baby emu.
The one on the left, what is that?
It's a baby.
Ostrich?
Not an ostrich, no. It's living in South America. It's called a rhea.
Oh, really?
Rhea. Yeah, it's called a rhea. Yeah. So that's amazing that we have animals like this. It's also, of course, with plants, and you have succulents who look like cactus but are not cactus, and so on. But of course, as we said today, that DNA itself is important. I mentioned it, for instance, by the evolution of flowering plants, that it is thought that duplication of the genome, so the total amount of DNA influence the evolution, and a nice,
No, that's not the point.
That's the one. Yeah, thank you. A nice example is also the evolution of fishes. If we look at all-time fish here, like the coelacanth and the Polypterus, the sturgeons and the alligator pikes from America, the amia, there are only about 40 species. But if we look at the fishes where we think of, if we hear the word fish, the so-called teleosts, there are more than 24,000 species. And the idea is that during the Paleozoic, in the ancestry of the teleost fishes, there was a whole genome duplication that took place. So the more DNA you get, the more chances of evolution. Hence the enormous number of teleost fishes. So DNA itself is, of course, influencing the evolution, the speciation. And a nice example to see that are the big African lakes, like Lake Victoria and the Malawi lake. Perhaps you have heard of these so-called cichlids. They're famous fishes. People who love aquaria like these fishes as well. But in these great lakes in Africa, and Victoria, Tanganyika and Malawi, there is a huge amount of species of these fishes. And the point is that they are living in the same environment, and yet there are so many species. So that's an illustration of the fact that an enormous amount of DNA triggers a huge evolution, and the idea about it that the relationships between males and females, so males displaying themselves to attract females, that was a driver of evolution. But as we said before, environment itself is also triggering evolution. And if we start with an ancestor mammal, for instance, we can say, for instance, that whales are not related to wolves, although they like meat, and they don't look or act like each other, and then we call them divergent evolution. So if you have an ancestor of a certain group of animals who have the same ancestor, but the results, the descendants, behave very differently or look very differently, then we have divergent evolution. An example, for instance, is also what we told yesterday, that bats and horses are distinctly related. That's different, this divergent evolution. So the conclusion is that the pressure of the environment drives evolution, but if you compare whales and sharks, for instance, they are living in the same environment, although not related, then we call that convergent evolution. And there are very There are of course famous examples, I think you know them. What is meant is this. We see several groups of vertebrate animals who are adapted to a marine life, a marine environment. So the fish form, the shark form is very ancient, and there are still sharks. This is a very good model, so to say. Once there is an organism that's very well adapted to its environment, the chances are big that it is staying alive, so to say. So in a way you could call sharks living fossils. But other marine vertebrates who went to the sea secondarily are descending from ancestors who lived on the land, like the ichthyosaurs. This is this is very cute ancestor of an ichthyosaur. It's not so long known. I think it's known only after the year 2000. So Cartorhynchus, an interesting animal. There are nice publications about this. If you are interested, you should type in Google this name, Cartorhynchus. There are very interesting publications about it. Because they were giving living birth, and in these creatures, when the young was born, so they are ovoviviparous, the head was coming out first of the mother, but in ichthyosaurs the tail is coming first from the mother because they need to breathe air, they don't have gills. And it's a parallel evolution with whales, like ichthyosaurs in whales. When the calf is born, the tail is going out first because otherwise the young is too long underwater. But as you probably know, also the whales have ancestors who were living on land. So the environment is driving evolution, then the results more or less are all fishiform animals. Perhaps the most famous example of convergence is this. I think you all know this animal, don't you?
Tasmanian devil.
Sorry?
Tasmanian wolf.
Tasmanian wolf or thylacine. Yeah. It's a marsupial, and well, they don't live. Unfortunately, they don't live anymore. But the resemblance with bulls are remarkable. Yeah. They don't live anymore. They have tried to isolate DNA from an embryo who was in a jar, and put it in the egg cell of a Tasmanian devil. I think you know the Tasmanian devil from Tasmania, a carnivorous animal, but it did not succeed. It's too bad that it died out. And if we look at the history or at the situation, then in ecology we speak of niches. You know the term niche, I think all of you know the term niche, and it's a life form adapted to its ecological function, like a burrower, an anteater, mouse, climber, glider, cat, wolf, all adaptations to their environment. And you can also make a division in the food that they use, carnivores, omnivores, herbivores. And we see here a striking resemblance between the so-called placental mammals and the marsupials. Every placental mammal more or less has or had its marsupial counterpart. So that is a very nice example that the environment is driving evolution into a certain direction. But now we have only, with one exception, we have only marsupials in South America. But you all know this one, I think, the opossum from North America, very cute animal. But opossums is a very old model. If you look at the ancestors of marsupials, and then you could call this a living fossil. The ancestors of the mammals, the placentals and the marsupials look more or less like this. Unfortunately, it's a little bit too bright here in this room, but this is a very nice fossil of an opossum-like animal from the famous quarry of Messel in Germany, from the Eocene. And this is an opossum-like animal from the Cretaceous of Maastricht. It's based on this tooth. That is typical for a marsupial opossum-like animal. So that is to say that in the Mesozoic there were of course already marsupials, but they were not only in Australia but also on other continents. And this slide is showing that more or less. It is thought that the ancestors of marsupials who looked like opossums originated in South America, and we have all kinds of forms. There were many marsupials with all kinds of ecological niches, and they, if you compare that, so it was in the Cretaceous, about the mid-Cretaceous. If you compare that with this position of the paleogeography of the continents in the mid-Cretaceous, then you can see that the marsupials were able to reach North America, Europe and Asia, and through here a land bridge through Antarctica they could reach Australia. And it seems that Africa was isolated already then, but because as far as I know there are no fossil marsupials in Africa. So in the tertiary, late Cretaceous and tertiary, there were also many marsupials in South America, and only the opossum form, the opossum-like animals survived in the Americas, and on all continents the marsupials died out. In the Eocene they died out in Europe and Asia. So that's why only in Australia the marsupials are left. And if you compare the evolution of marsupials with placental animals, then the radiation, the evolution of several forms, the radiation of placental mammals was slightly later than marsupials. So the placental mammals were just too late to go through Antarctica to Australia. So that's why before man evolved, there were only marsupials in Australia and no placental mammals in Australia, because the placentals were too late in their evolution to reach Australia. We know the Tasmanian wolf, but this is also a very striking example of convergence. There was even a saber-toothed cat, a marsupial saber-toothed cat, living in South America. Very nice skull. So you know about the term niche. You could call that an ecological function of a large predator, and as well as in the placental forms, as in the marsupials, that evolution took place to get a large predator, and the result was at first glance the same. Here a comparison with the skulls. This is a skull of a saber-toothed cat. This is the one from Thylacolchmeles. And you see that there are, if you look at the skull, there are of course very big differences. This here, this part of the skull is full with the root of this canine tooth. So the canine tooth in this marsupial saber-tooth was growing during its entire life, and this part is fully occupied by the root. You see also that the brain case in this animal is smaller than the brain case in a placental saber-toothed cat. If you look, for instance, in old literature, in old zoological literature about marsupial wolves, Tasmanian wolves and ordinary wolves, then it is often written that the marsupial wolf was much more stupid than the normal wolf. But I don't think that is true. I don't think that was true, but nevertheless. It is supposed in earlier days that the marsupials were not so smart as placental mammals. But there is even another interesting thing where you can see how environment is driving evolution. The placental saber-toothed cats evolved at least 3 times. So you can see it here. Huh? There are different geological periods, and we have different saber-toothed cats. So these are not, for instance, the Nimravis is not the ancestor of Barboropholis, which is not the real ancestor of Smilodon. They evolved at least 3 times during evolution. So that is a very striking phenomenon. And here we have some kind of pedigree related to the time. Here in the early Cretaceous, or even in the very early Cretaceous, about the end of the Jurassic, we have here the split between marsupials and placentals. And of course this is the marsupial line resulting in Thylacoschmilis, the marsupial version of the saber-toothed cat. And here we see, for instance, Nimravis, here Barboropholis, and here Smilodon. So you see in the placental branch there are 3 times that saber-toothed cats evolved. And the paleontology, the evolution about mammals is very interesting. If you look at this graph, it's plotted the Mesozoic mammal genera known to science, plotted against the time, and the time unfortunately is running